Hello and welcome to Roboconhelp India live webinar, which is the third in the series of robot design methodology. My name is Manish Chauhan, the Chief Editor at Roboconhelp India. In the previous two live webinars, we had talked in detail about the design process. We learned about the design as a problem-solving technique, or in simple words, we can understand that design is a decision-making process, where one needs to properly define a problem. So from previous live webinars, we have also understood that one needs to build the skill of observation to be a good designer, who is patient to understand its iterative nature. In this regard, we have understood the design problem is first sensed at the user end. One goes through various um, solution alternatives after defining a problem, and at the end of the design process, one chooses the most appealing design alternative to solve the sense problem. And this we had understood over here. To make sure that the correctness or the suitability of the design solution, one must make sure that solution alternative search must be done thoroughly. So with this, we can closely understand that design is an iterative process in nature, and this we understood with the PDCA cycle. Yes, the iterative nature we have understood over here, and we discussed in detail about how the design goes from clarifying the task to searching of various concepts and fixing of a concept. And we further refined it with understanding the PDCA cycle. Finally, we applied the process on various case studies, like we had discussed about Robocon 2013 statement. We had also discussed about various case studies in a second live webinar where we learned about the design of a chair for people who cannot sit straight without support. They need some support at their back and the spinal cord. Or there was some design of some body cover for maintaining body temperature of various infants who take birth and then they have no body temperature to control. So now we have to focus on a second step of the design process, that the exploration of design alternatives. So this live webinar is based on the book by Professor K.T. Eldridge on design, creation and artifacts in society. So exploration actually involves consumption of resources, which is basically will be evaluated, and then many of the alternatives which are evaluated will be eventually abundant. Exploration inevitably involves consuming resources to develop and evaluate alternatives that will eventually be abundant. We would of course prefer to avoid this wasted effort and just pick up the right answer directly. Suppose if we share an example of a design problem where the problem can be solved without exploration. Just like if you want to design a beam. Because the beam design problem is simple, well defined, highly constrained, and because it is informed by 2 centuries of development in engineering science, it can be solved without exploration. Suppose if you have to make a structural element spanning between some distance and to support 2 antennas on some station. So antenna can be mounted in the center of the span and will apply some inertial loads, say up to 100 newtons perpendicular to the axis of the beam. So the beam may not deflect more than 2 millimeters under that load in order to maintain the signal quality and limited vibrations. So what we are actually I'm trying to show out here is that the engineering science has already been developed, and the same problem it can be solved without exploration. But if the same beam problem is taken up in a different direction, suppose we say that why not choose a different element or material for this beam element, say titanium or steel or carbon fiber or plastic, or what should be the cross section? Why not have a different cross section of the same tube? Can't the walls of the beam be thinner in the middle? And what about the end support on the truss? There are so many questions which will open up the areas for exploration. And with this, you can understand that even though as engineering science has developed various solutions, but practical design problems can rarely be solved effectively without exploration. This we can further understand the way we feel exploration is essential is to find the optimized solution of a given problem. For this, first step one should follow after the problem definition, which we have learned in our previous live webinar, is basically representation and abstraction of your design problem. Suppose you have thought of designing any artifact and you really want to make it. So the first step after the problem definition will be you first represent or abstract, make a rough or abstract sketch of that artifact on paper. This is generally a brief rough sketch of an intended solution for any design problem. Just like the design problem which we framed in the last live webinar, and we used the Toyota quality management technique of 5 whys to define a design problem. Like we chose a problem statement like pick and place of a 10 kg object with the distance about of 100 meters. So as we already know that design needs to be understood from the user needs to solve the problem. Hence, we went to various users and considered few key user needs in robots for which this problem statement could be solved. So I personally met many people and realized that what needs will they require if they really would like to have this robot. Please note the list is inexhaustible and very few users' needs are considered for this process for basic understanding. And these needs were like this. The robot should reorient itself quickly. The robot should be able to adjust its height automatically. The robot should not slip on ground. And the robot should have a robotic arm on top to pick and place and maneuver quickly. So this list goes on, but I've just picked few very prominent key needs which users gave to have in this robot. So then when I personally met users and I framed these new needs, so the next step which one requires to do in exploration is to decompose these ideas to form your design space. This basically works in 3 ways. One is you go to users, as we have already understood through the block diagram. Go to the users, understand their gap, what kind of needs they require, and you just explore in those needs, and you find out solutions which actually solve or are able to satisfy those needs. Otherwise, there are 2 other methods as well, which are exploration based on sequence of operations. Such kind of operations are a sequence of operations are basically useful in designing services for any product. Suppose there is a car rental service, or there is a bus rental service, or a hotel management, hotel room service. So basically, those services are designed by this sequence of operations. There's one more method of exploration, which is functionality by exploration by functions of various parts, which form the sub-assembled parts, which form combined together to form the complete artifact. For simplicity of understanding, we will be focusing completely on key needs exploration method. So let's come back to how this method will help us to solve the basic problem which we have framed in our previously, just like to design a robot for pick and place robot for 10 kg object. Now please understand this, before I move ahead, I would like to tell you that these needs are actually given by people who are somehow novice, because a person who is picking up 10 kg object requires a lot of effort to do that, and a robot, if it is required to do that, it really needs a lot of effort to move across 100 meters and picking up that object. So this statement is basically can be reframed to have a lower mass weight to be picked in place for a distance. But basically, even if it's lower mass, the needs will be obviously similar to what we have framed over here. So once we are coming to the next step of exploration, where we are decomposing the ideas to form a design space using the key needs. So how does this method work? This method works like this. You have a big design problem and you break it into subparts. Say over here, you have say 3 subparts of a big design problem, say A, B, C, and you solve these subparts individually without considering the other subparts. Just like if you solve this subpart 1 and you have certain some solutions which are framed over here with this triangle. If you try to solve subpart B, you have various solutions, say in this square form, and the subpart C can be solved individually, and you have some alternatives to solve these subparts. The last step of this method will be you integrate all these solutions and combine them to form various solutions. Just like you choose one of the subpart 1, one solution of B, subpart 3, one solution of C, and you just combine them to form one solution. Similarly, you may choose other subparts to form another solution. So if we find out the design space by following this methodology, you can understand that 7 alternatives are available in solving subpart 1, 7 are available in subpart B, and 8 are available in subpart C. So in total, we have 392 possible combinations of solving this big design problem. It's a very powerful technique to solve any design problem or explore alternatives which will be useful in solving any design problem. In our case, we are actually designing a robot for pick and place operations. Now, similar methodology has now been applied to the same problem. Just like we have just chosen 2 user needs. As we know that we had framed approximately 4 user needs, and we are just now focusing on 2 user needs to illustrate the methodology, how this method can be used, and this is how we had solved it. We chose 2 subproblems, like the robot should reorient itself quickly, and the robot should have a robotic arm and maneuver quickly. So we came up with various alternatives which are already existing, and we did some creative combinations, and we found out few solutions. Just like we have a 2-wheeled solution, which is simply a differential drive system for driving any robot. And we chose another configuration. We had 4 wheels mounted on motors and placed in a cross or a plus cross section, a triangular cross section where motors are fixed to wheels, a belt shaped cross section, and a simple caster wheel attached in front and 2 wheels attached at the back. And this forms a simple 3-wheel combination. Now, for solving the subpart B, where the robot actually has some robotic arm, so we are basically focusing on the robotic arm. What should be the configuration of the robotic arm? So we have 3 degrees of freedom robotic arm, 2 degrees of freedom robotic arm. Even in 3 degrees of freedom, we have various alternatives. Like over here, the base is rotating about its own axis. Earlier, it was not rotating about its axis. A 3 degree of freedom robotic arm may also have a linear slide, or a 4 degrees of freedom robotic arm. So now we have all in all 5 alternatives to solve the first concept, subpart, and 5 concepts to solve the subpart B. And if we recall, we have not yet addressed other 2 subproblems, user needs, but still we have 25 available solutions to solve this. So now what we have done, we have treated each user need individually and tried to solve it. Our focus is to turn every possible solution upside down and do not leave any alternative unexplored. And with this method, we form a huge design space solution to explore and find solutions. But after we have found one, we just have, the final step will be to integrate those solutions. And just to illustrate, we can just show like we had integrated one solution with only these two subparts under consideration, and we chose a simple 3D robotic arm placed over a three-wheel configuration of robot. So now over here, what we have learned is that we are basically learning about various design problem techniques, and we had initially learned about framing a question, problem statement, and now we learned about a methodology where we can explore alternatives to solve a particular design problem. And this one of those alternatives which we have kept focus on is the key user needs. But to further refine these exploration strategies, it actually looks to be a very small part of the design process. But in reality, we have to explore to the depth. And there are few methods by which you can basically refine those alternatives and choose the correct alternative, because we have a huge design space. Now, out of those huge design space, one needs to choose the correct alternative. So we are giving you a structured approach where these alternatives can be explored. One is simple hierarchical decision. So this decision is basically made to reduce those design space such that you have collective alternative solutions which are most suitable for solving this problem. So one should sketch various concepts keeping the constraints in mind. But even if one does not do, the choice actually made sequentially after considering the constraints reduces the design space to a limited number of alternatives which actually satisfy the constraints. And this design space can be formalized and limited where the alternatives are limited, and one can sequentially go and follow the steps of choosing the right solution. Just like in our previous case, we had talked about various configurations for robot maneuverability, two-wheeled robot system, three-wheeled robot system, or even more. Just like if we closely look back, so we had various alternatives for the robot orientation and the maneuverability. So now if there is a design constraint that you just need a 3 degrees of freedom robotic arm, or the number of wheels should not increase more than 4, or the power requirement should not be more. So in that case, the constraints define or block your design space to a limited solutions where you can just choose from. Other form of other form of exploration is parallel exploration and selection. So in this methodology, you arrange all the design alternatives in decreasing order of importance and increasing order of effort. And from the designer's perspective, you can just choose the right solution where you have optimum amount of design effort and the least possible cost or importance available, or most important actually solution which is available to you. So now designers can basically focus on high impact and low cost designs first. This actually also reduces the cost, and low impact decisions are avoided for later available choices. So what if we just illustrate on this point, what we do is we have various design solutions and you parallelly place them side by side in increasing order of effort and decreasing order of importance. And from there you can just compare, and based on your discretion and expertise level, you can choose the right solution. Causal relationship is basically another methodology of a technique of finding the right exploration. One actually needs to know the dimensional relationship between mating and assembling parts. Just like if in this case of our robot for pick and place operation, one needs to have the causal relationship between the size of the chassis and the size of the wheels, or the size of the motors, or the size of the robotic arm? Will it go beyond the center of gravity of the whole structure, or the robot will topple off? So these simple questions must be can be solved or can be answered by actually having the correct understanding of causal relationships. And this one exploration techniques will separate a novice from an expert designer. This also carries certain amount of aspects between of aesthetics along with technical dimension and sizes. Better informed decisions can be made with this strategy. Now, the last methodology in exploration is you see basically the existing artifacts which are already there in the market, or if already been designed by other designers. In our case, we have to choose a design a pick and place robot. One needs to have a good understanding of robots, and the understanding develops by looking at already existing artifacts. The existing designs are basically jewels for designers. It reduces the efforts of reworking the same solution. If you are observant about other people's work, you do not need to design it once more. It's just a group activity. You just choose one solution available, and it acts like a template for you to modify as a designer. So with this, basically, you have understood that exploration requires dividing the big subproblem into various subparts and individually solving them to find solutions, just like we have illustrated over here, and you just integrate them to find the correct and the final solution. So in this live webinar, we have briefly understood about the design exploration methodology, and in the next live webinar, we will learn about applying the same technique on Robocon problem statement, as we are understanding this technique and practicing it in the huge activities. So thanks a lot for being so patient and listening to our live webinars frequently, and we wish to give you wish all the best for your future robotics journey, and thank you for choosing Robocon Help.